Okay, so I'll get these assignments back to you early next week, and what I'd like to do is to give you we'll just encapsulate the rectangular, normal tangential, and polar coordinate stuff today, and then start actually working several problems out maybe in normal tangential coordinates, and then get going on solving some problems in polar. All right? So let me summarize over here on the small board, first of all, those governing equations. If we're in our rectangular system, we have a position vector that we know is xi plus yj. If we're in the normal tangential coordinate system, I'm waiting for the camera to kick over to this screen here. Here we go. Okay, so if we're in the rectangular coordinate system, the position vector is given as xi plus yj. If we're in the normal tangential coordinate system, we know that that pair, the tangential and the normal, are on the path. And so we have no way, unless it's referenced to us somehow, we have no way of knowing where we are as far as the position goes in the normal tangential. But in the polar system, where we developed the equations on the last class session, the position vector was given to us nicely there as simply the distance from the pole times a unit vector pointing from the pole out through the point of interest. So we start there. Then we develop the velocity equation, and the velocity was simply in rectangular x dot I hat plus y dot j hat. And now we're on the path associated with the velocity. So in the normal tangential vector for the velocity, we can write that as the speed being carried by the particle in what direction? The speed being carried by the particle in the tangential direction. Okay. In the polar, the velocity profile, remember where this is coming from. It's coming from, let me go ahead and draw the reference figure. So let's say that's the path going that way. In the polar system, here's where we are on the path at this location at some angle theta, and our unit vector is pointing out there radially. We define in the direction of increasing theta, perpendicular to r, a unit vector theta hat. The speed is then a tangent to the path that we know. So here's the velocity or the speed. There's our velocity vector. And you can see pretty clearly on this picture that there's a component of that velocity that is radially directed and another component that is theta directed. The r component, the radial component, is the telescoping effect, or the rate at which this length is changing, the radial component of that velocity. So that's simply r dot in the r hat direction. Then there is a pseudo-rotational type of term that's pointing in this theta hat direction. It's that component of the velocity that's in this theta direction here, v sub theta, right there. And that is similar to what you've learned for rotational motion. In rotational motion, we know that the speed on the edge of that, in the sense of pure circular motion, the speed is equal to the r theta dot type of term, or r omega. So this is a nice way for you to sort of think of and trying to be able to remember what the velocity is. It's got this telescoping kind of component of velocity, which is the expansion or contraction of this length, r dot. That's that term. And then this term is r theta dot, a pseudo-rotational kind of a term. So plus r theta dot in the theta hat direction. So we now have three ways of describing the velocity depending on the coordinate system that's going to be most convenient to use for a particular problem. Then, of course, we need the acceleration. It's elementary in the rectangular form, second derivative on the x displacement in the I hat direction, second derivative on the y displacement in the j hat direction. And then our acceleration in the normal tangential is a little more complex than what we saw here in rectangular. It's going to be, it has a normal term which points which way? The normal points back, points which way? Towards the center of curvature. And that term, if you're on a curved path, how do we usually write it? How do we usually write that normal term? V squared over rho. V squared over rho is that normal term pointing towards the center of curvature plus a tangential term, tangent to the path. And this is the one with the blinders on, right? The tangent to the path is the one with the blinders on, and you're just looking down the path as you go. You can speed up or slow down, can't you? You can accelerate along the path tangentially. And how's that relate to the speed, v? Just the time derivative of that, v dot. Everybody with me on that, conceptually? Okay. These equations, and I haven't written the last one yet, which is our acceleration in the polar form, these equations are just absolutely fundamental, and hopefully you'll do enough problems that you'll remember these things. Like you know your phone number, or your name, social security number, things like that, okay? So these are really fundamental. Now, what we developed at the end of the last class session was then the kinematic relationships for polar coordinates. And we came up at the end of class with the time derivative of this thing, which involved, it got a little bit complicated because we have two time-dependent functions here. And over here we have three time-dependent functions, and we needed their derivatives. And so then what we did is we went ahead and used the product rule on it, and then also discovered what the time rate of change of these unit vectors were. And then we tidied up the terms and collected them. And we ended up in polar, we need a little more space for that acceleration to have a radial component of acceleration. And I'd like you to think about what this is for a second so that you can learn how to remember this. If you're talking about the radial acceleration going out or away from the pole, then you would expect it to carry what? Related to this length as far as the acceleration goes.
X and Y components?
We're not going to go back to X and Y. Let's just stick with R and theta. But I'm just talking about in this direction. Doesn't it seem like there should be a telescoping kind of an effective acceleration?
Same direction.
Which, in the same direction, which is, in that direction, it's R hat, but isn't it the second derivative of this length, R double dot? So it could be telescoping out, accelerating radially away from the pole, so there'd be an R double dot possible. And then, if it's on a curved path, kind of like I've drawn here, if it's on a curved path and not going straight out from the pole, then you would expect it to have something, a pseudo type of term pulling back towards the pole, wouldn't you? okay, to counteract possibly the r double dot going out. And what that is that's your, it's coming directly back towards the pole, and so it's negative, and it's typically written as r theta dot squared. So we write the r-directed acceleration. Here's the telescoping kind of an effect, r double dot, minus r theta dot squared. That's in the r hat direction. And then we have to add to it the theta-directed term of acceleration. This is made up of r theta double dot plus another one, another term that is oftentimes difficult to comprehend. It's 2r dot theta dot. And those terms are additive, and they're in the theta hat direction. So that's the acceleration equation, pretty complicated in your polar coordinate system. Okay, now what I'd like you to do is to look in the textbook at this geometric interpretation found on this page, page 69 of your book. I think they've done a nice job here referencing this geometrically. Their drawing is a little better than what I could do on the board. So if you look at this expression or this drawing, and notice this is the location of the particle while it happens to be on the path up at some point on the path, And these lines that you see drawn here are heading back towards the pole, So here's the particle, and this lower line you see here is in your r hat direction, and you can see there is a radial component of velocity out along that. Now, that radial component of velocity could grow over a slight change in time, And that's what gives you your r double dot. In that same direction, in that same radial direction, look up here. There is a component of this theta-directed term that is actually pointing back towards the pole. See that little down left directed component right there? And that's going to be the r theta dot squared term, what I call the pseudo normal kind of term. That's where that one's coming from. So it's the sum of this r double dot type of term created from this differential minus that one, which points back towards the pole. Now, in the theta-directed form, you have a differential radially here in the theta, or sorry, not radially, but in the theta hat direction. Here's your velocity component in that direction, and there's the differential change in that, pointing out here. And from that, the time derivative of that is going to give you your r theta double dot term. And then we're also going to pick up, when you take and look at the time derivative going on with this differential component right here, you get two terms showing up. And that's what gives you that very last term in the theta-directed acceleration over here, r dot theta dot. And there's a pair of those, which are additive. And this term is called, do you know what this is called from your physics background? here's a hint that'll take you back to your physics experience. If you're on a rotating body, you're going to have some theta dot. If you're on, like the Earth, or a merry-go-round, you're on a rotating body. If you're on that rotating body, and you've got some r dot, now r dot represents what? Radial motion, doesn't it? So if you're moving radially on a rotating body, you're going to get a non-zero term here. If you're moving radially on a rotating body, you're going to get a non-zero term here. This is the Coriolis term. This is the Coriolis term. And we're going to talk about that in more detail later. So anyway, this board now gives you a complete summary of the kinematics, the vector kinematics for particles with 3 convenient coordinate systems. Okay, so I think it'd be worthwhile to go ahead and work a problem out or two now, sort of see how we fit this stuff together. Before I do that, sorry about changing gears here. If you go to the next page in the book, they actually show us how the acceleration, they do a nice job here showing us how the acceleration terms play together. We've spoken of this before. If you're on a curved path, then we know there has to be a component of acceleration that is towards the center of curvature. So the acceleration is always going to have to be on the inside of the curve or no further out than tangent to the curve if you were on a straight line. Okay? So there has to be an inward component. So the acceleration is always going to be somewhat inward of the curve, on the inside of the curve. Now what they've done here in this illustration is they've said the particles here at position A, and you can see they've decomposed this acceleration vector into a radial component made up of those 2 terms we spoke of, and a theta-directed component made up of the r theta double dot. Oftentimes we call that r alpha, right? R alpha plus the Coriolis term, Okay. In the case of circular motion, look what happens here. You're going to have no radial component of velocity if you're in circular motion. And your theta-directed velocity is your familiar r theta dot, or oftentimes written as r omega. And then look what happens on the acceleration. There is no r dot on the acceleration. So if there's 0 r dot, then that means r double dot is 0. So you only get this acceleration term, which is pointing which way? Look at this term. Back towards the center of the circular motion. Back towards the center of the circular motion. The other way we oftentimes write that is what? Negative v squared over r. Negative v squared over r, right there. Or sometimes we write it like this, or write it as minus r omega squared there. And then this is the tangential component, in circular motion, tangential component of acceleration, r theta double dot. Oftentimes written r alpha. Okay. Let's do a polar problem, and then we'll do something else. Let's look at this one. and I want to cover up something here for a minute. Okay, it's number 138. So we're the observer on the ground, and we see an airplane flying, coming towards us, and going to pass right overhead. It's coming towards us, going to pass right overhead. I'm going to zoom in a little more on this. Okay. They describe to us that the plane is traveling in a straight line as shown at a constant speed, which means that the plane's acceleration is 0. The plane's acceleration is 0. Determine the signs, plus, minus, or 0, for all these different components of velocity and acceleration. For each of the 3 positions, A as it's approaching, B as it's directly overhead, and C as it's already passed over us and heading away. And you have to be careful as to how theta was defined. Okay. So, we're looking for plus, minus, or 0 for these different components. So by looking at this in position A, R is positive, right? R is clearly positive. R dot. R dot.
It's getting smaller.
R dot's getting smaller, isn't it?
Yeah.
Isn't R dot contracting there?
Yes.
Okay, good. Now, what about R double dot? Think about that. R double dot.
As the plane gets closer to you, it's going to be getting smaller at a faster rate.
As the plane gets closer to you, it's going to be R is going to be getting smaller at a faster rate,
A slower rate.
or a slower rate.
It says you go away, it'll be
Slower rate.
Okay, so what's correct there on the R double dot?
It's going to be positive.
R double dot is positive. Positive points which way? R double dot positive points which way?
Oh wait, it's negative. It's like
Away from the pole, outward. R double dot positive, pointing away. Okay, so you're saying it's positive there, and then we'll talk about B and C in a minute. What about theta at this location? Theta is clearly defined right here. Looks like a positive defined angle. I can answer that one, okay? Theta dot, the time rate of change of theta, is it increasing or decreasing?
it's increasing.
Theta dot, is the angle growing with time?
It's getting.
Yeah, angle's growing with time, so theta dot's going to be positive. Now, is theta dot growing as it moves towards B? Is theta dot growing? Now, what we're trying to get a handle on is theta double dot.
Theta double dot is going to be constant.
So is theta dot is growing, right? So we know, I'm sorry, theta is growing, so we know that theta dot is positive. But what's theta dot doing? Is it changing as it moves towards B?
I'm trying to imagine it's starting out.
The plane's moving at a constant
The plane is moving at a constant speed.
So the change in angle will be
So watch the pencil point. The plane is moving across here at a constant speed. What if the plane was way out here to the right? Is theta growing very quickly? Way out here to the right, coming towards us? No. It looks like the plane might appear to us to be almost stationary in the sky until it starts getting closer to us. So we're going to see, as the plane starts to get closer, we're going to expect to see theta dot increasing, aren't we? So we would expect to see theta double dot as positive. positive. Okay, let's jump to B before I put everybody to sleep. What about R?
R is 0, or not 0, it's positive, but it's not
R is
changing.
positive, right? And it's not changing much when it's right above us here, is
Right.
it? R is staying pretty close to that minimal value right there shown. Okay, and so R dot at B is
0.
0. See, R dot was negative, wasn't it? Out in here, wasn't R dot negative? And then R dot becomes 0 here, and then as it moves out and it heads towards C, R dot is positive. So this is the kind of thing you want to do with these problems, is you want to fiddle with them to try to understand the physical situation, sort of have a sense of it. And then, let's say you don't have a sense of it. If you don't have a sense of it, what do you want to do? Find your instructor? Ask your friend? No, crank out the mathematics. Crank out the math and see what it tells you. The math will give you the insight. If you can't see it, the math will give you the insight unless you screw up the math. Okay. So let me just pull away here. I worked up a little summary of this that we can see clearly at A, B, and C, the R's are positive. R dot was negative when it was approaching us, 0 when it's straight above us. R dot was then positive. The accelerations, R double dot, positive.
Why is R double dot positive?
Oh, why is R double dot positive written here?
It shouldn't be.
Okay, let's have a little question mark on that. We'll go play with the math a little bit. Okay? And then here we have theta clearly positive everywhere. No problem there. And is theta dot positive everywhere? Is the angle always growing?
Yeah.
As it arcs across, the plane arcs across above us, the angle's growing. And then here we have a positive theta double dot. We're seeing theta dot increase as it approaches us, 0 at the top, and then theta double dot becomes negative after the plane passes overhead. So we have a little bit of confusion, at least about what I have written here regarding the R double dot. And where is the confusion? On which point here? What do you want to question on that?
No, it just, yeah.
R double dot at A. Okay, so let's see if we can set that up and look at it. So here's the plane at A,